All right. So we are going to do a few more examples with this sampling distributions for one sample mean. So quick review from the last lesson. So the sampling distribution of the sample mean. So first of all, remember what this means. This means that if you take lots of samples of a specific size, so lots of samples of size, say n could be 100, 1,000, 50, or 20, but lots of samples of that size. This tells you how the mean will vary across your samples. So for example, if I repeatedly take groups of 20 UAF students and find their average weight, how much is that average going to vary among groups of 20? Does that idea make sense? As opposed to how much do the weights vary in a group of people? Okay, how much is the average going to vary across a group of a specific size? Okay, that's kind of the difference here between the other stuff we did. It's like you're talking about a mean of a mean. You take a sample, you find a mean, and then you do that lots and lots of times and do a mean again. You're meaning a mean. Okay. Now, if your populations and this thing you get is going to be approximately normal, which means things like your 68, 95, almost everybody rule applies. And it's normal if a couple things happen. If your population is bell-shaped, like we can pretty much assume weights are bell-shaped, right? Ish. We'll pretend they're bell-shaped. And then the distribution is approximately normal, and regardless of the size. If your population is not bell-shaped, you must measure a quote-unquote large sample, and I agree this large is a bit arbitrary, but your book says n equals 30. Okay, so 30 is what they call large. Okay, so this probably shouldn't say what, it should say when. Spell check doesn't catch those things. When a population of observations is bell-shaped and or a large random sample is taken, we define the sampling distribution to have mean mu and standard deviation sigma. So, and then, this shouldn't be defined. Okay, then the mean of the sampling distribution is mu. And then the standard deviation of your means, remember what that formula was from last time? Sigma over square root n. So sigma is the standard deviation for the original population, like how much does weight vary. This one tells you how much is average weight gonna vary in a group of size n. Bigger n's, less variation. And the standard error, remember that's what you get when you estimate the standard deviation. So that's S over n, where S is the sample standard deviation. Oh, just FYI, tomorrow we'll learn like the last of these formulas. The back of your, Wednesday, tomorrow in Class World. We have 3-day weeks, right? At the back of your chapter 9 in your book, they have a nice summary with all the formulas in it. Might be a good thing to put on a note sheet. Okay, just great little table. Okay. So how is the standard deviation sigma different from the standard deviation of the sample means SD of X bar? And let's pick a specific example. Let's suppose that the variable X is the weight of a random guy at UAF. That's like the random variable. It's somebody's weight. So do you buy that sigma describes the spread, and we'll say variability of weights of men at UAF? Do you agree with that? Sigma is your standard deviation, right? That would tell us how much variation there is in weights of guys at UAF. SD of X bar, that's sigma over root N. Is that the same thing? No. So what's that going to tell me? The spread of what? I just couldn't hear I couldn't hear the first part. Sorry, the spread of.
The spread and variability over the total amount.
So spread and variability. Let me say of X bar. Does that make sense? Of a mean for samples of size N. And X bar would be average weight. We can use that to like ask the question, well, is the hockey team's average weight bigger than a random average group of people at UAF or something like that? Because they'd be like, they say like, are they actually, is this group of 20 people actually different than any other random group of 20 people? So it's looking at averages as opposed to individuals. I think that's a good distinction. Okay. So I don't know why this book's on a weight kick, or I swear I'm not obsessed with weight. I really am not. But suppose we have a hypothetical weight loss clinic, and hypothetical and population mean and standard deviation of weight losses were 8 pounds and sigma was 5 pounds respectively. We're supposing we know these true values. So on average, people go to this weight loss clinic and they lose 8 pounds. And then so that means some people are actually gaining weight, right? Mm-hmm. So, but it happens. Who knows? Maybe they needed to because they were anorexic, okay? So we'll just pretend.
How are some people gaining weight?
If they go to a weight loss clinic, I don't know.
Maybe if you're exercising, you're gaining muscle.
Well, okay, because if you look at this mu is 8, and the standard deviation is 5. So that means 68% of people lose.
So like 2 standard deviations away.
2 standard deviations away, you'd do 8 minus 10, which would be -2, which would correspond to a weight gain of 2 pounds. That's how.
Yeah.
Yep. And so I don't know if that's reasonable, but I do think that some people that go into weight loss clinics don't actually lose weight. It happens. It's depressing, but it happens. Okay, so suppose we're taking random samples of size 25. Find the mean and standard deviation of the sampling distribution of X. Okay, so first thing, the mean. The mean is the same as the population mean, which is 8. And the standard deviation of X bar is sigma over root N, which is, sigma is 5 over root 25. It's going to be 1, yeah. Okay. So 68% of X bar are in what interval? 7 to 9. Do you guys see how they got that? If I say 8 plus or minus 1, does that make sense? Plus or minus 1 standard deviation, which in this case happens to be just 1, right? How about 95% of your means are in 6 to 10? So that's 8 plus or minus 2, right? Officially 2 times 1, which is just 2, right? And how about 99.7%? Are in 5 to 11. And this thing is true if your sample size is n equals 25. So if you had a group of 25 experience on average 15 pounds of weight loss, would they be special? That would mean they'd fall way outside this 5 to 11, right? Does that make sense? But those intervals mean that your means for sample sizes of 25 are going to fall in this interval sometimes, this interval most of the time, and the last interval pretty much almost always.
Would it be special even if they were just 12 pounds?
Even just being 12 pounds would be special, exactly, yep. So with the next one, what I would like to do,
Would you take points off, like, on a test if you wrote the interval backwards, like the bigger number on the left, small, right?
Probably not. I don't know if your grader will though, okay? Like it's hard to legislate all those things, so try to put the smaller first and the bigger. But tests are tricky and everybody has like flustered moments. But in intervals, the lower number is always written first. You can also write it with a 2. You could just say 629. That's fine as well. Okay, so repeat part A using sample sizes of n equals 100. What happens to your intervals? So does the mean change?
No.
No, the mean is still mu. It's still 8. How about that standard deviation of x bar? Is that going to be different?
Yes.
Yes. So sigma over root n, 5 over root 100, which is now, which is 0.5, right? Okay. So in this case, if we take sample sizes of 100, 68% are of x bar are in what interval?
7.5 to 8.
Yeah, 8 plus or minus 0.5, or 7.5 to 8.5. How does that compare to the interval you did in example 1?
A lot smaller.
It's quite a bit. It's 1 pound wide versus 2, right? How about 95%?
7 or 9.
Are in 8 plus or minus 2 times 0.5, which is indeed 7 to 9, sorry. And almost everybody are in between 6.5 and 9.5. And the kind of idea here is that if you take big samples, your average kind of stabilizes and doesn't vary much from one big sample to the next big sample. So for example, like I teach somewhat big classes. If I average over a big class compared to a different big class, they might not be all that different. But with small classes, there can be lots more variability. Have you guys heard of No Child Left Behind? That little, okay, so that is one reason that they have scoring metrics to score various schools. And it's one reason that's hard for big schools to be scored as like good schools, because the fact that they have a big sample size means they end up being just sort of average. But small schools end up having a few great students who end up being outliers and they skew their average up. So their statistics is the reason why all of the best schools and all the worst schools are little schools. It's not that little schools are better or big schools are better, it's that the statistics makes it easier for small schools to appear more successful because there's more variability in their mean performance. It's a smaller sample size. Okay.
Does that apply to when you, like, with the high school, like, if they take a test or something, they're like, oh, we scored one of the highest in the nation?
Yeah, it's the same idea. It is. It does. Yeah, it does. It does matter. Like, because the sample size matters a lot. If you have a big sample, you see you're reading, these intervals are not very big, right? So you should like all be super exceptional to fall outside of them. But when you've got small samples, there's a lot of variation. So yeah, that does apply to that stuff. So people have written sort of, anyways, so it's crazy how this, yeah.
Senior class of 3, only 2 of them took the SAT.
I mean, that's extreme, but even in groups of 20 versus 1,000. The point is that stuff like that makes it hard to compare a school of thousands to a school of hundreds. You'd have to really compare apples to apples totally in all ways, and that doesn't happen. So, all right. Draw a sketch of the sampling distributions, the potential sample means for 25 and 100. So here's how we're going to do this. Draw a horizontal line. Step 1. That's not a very hard step, right? Although straight lines are very hard to draw. I hate it when mine aren't straight. Put the mean in the middle. What was our mean? 8. Okay. All right. Now, the first, part A, our 68% were between 7 and 9. 95% were between 6 and 10. And almost everybody was between 5 and 11. And we're not going to be very, very specific about this, but except for one thing. These curves are approximately normal, which means they're bell-shaped. And the whole 68, 95, and almost everybody means that 68% of the area is under 7 to 9, 95% from 6 to 10, and pretty much area of 1 from 5 to 11. So it looks about like this-ish. And the specifics about how high that curve is, like this curve has a pretty complicated equation. We're not going to get into this class, but the kicker is that the total area under the curve is about 1. That comes from probability, remember that? Okay. So that's the n equals 25. I know you may not have more colors of pens because you lack a really cool iPad, but you probably could draw dotted lines for the next one, right? So what happens to the variability? What happened to the intervals when n was 100? They got smaller, right? So we had 68% between 7.5 and 8.5, right? So 68% from there until there. So what that forces my curve to do is to be taller. And that's because, I'll draw this in black, this area that I just shaded is 0.68, and the area from there to there has to be 0.68 as well, which means it has to be taller for it to be the same amount. So that's also 0.68. And then what was it, by 7? You're at 95% and 9. And I think by, what was it, 7 and 6.5?
6.5 and 9.5.
You're pretty much down to 0. I'm going to draw that a bit darker so you can actually see it. But the thing is, the total area under both curves has to be 1. It's just that for the first one, the x's range between 5 and 11. The second is just 6.5 to 9.5, so it squeezes it up and puts more stuff in the middle. And a bigger sample is going to make it even taller and smaller, right? Because a bigger sample means that these standard deviations are going to decrease, right? Which forces it in. Your textbook, this is an example from your textbook, they have a picture of this in there. Like they actually did it, like graphed it on a computer. It's much better than this picture, but that's the basic idea, is that it has to get, the curve has to get taller. And I'm not gonna really grade, how I will have your grader look at your curves is, do you have about the right width of them? Do you see what I'm saying? Like, do your standard deviations go out far enough? That's kind of what we're looking at. Okay, we'll change it from super fat to less fat. This guy. All right. I thought this was a great problem because we're in Alaska and there's tons of small planes flying in Alaska. Yeah? Okay. And you also know you should not weigh down small planes, right? Because what happens is you run out of fuel or you just don't make it off the takeoff, you crash. That's bad. So I have a friend who works for Alaska Airlines and another friend who worked loading bags, and they do stuff like this to figure out how much fuel to get on planes and how much weight. And there was apparently a plane that had a bunch of military people on it at one point in time, and they all had heavy bags. They didn't get charged for oversized bags, so the people fueling the plane didn't know about the oversized bags, and they almost didn't make it off the runway. And I think they had to stop someplace that was not planned to refuel. Like they knew once they took off they'd have to do this, but so, okay, moving on.
At least they didn't like almost not make it to the
Yeah, they didn't
destination.
like die or anything. It was just, math matters. Don't do wrong. Mistakes happen. Okay, so small planes cannot fly well. Something called the payload, which is people, luggage, and fuel, weighs too much. And suppose an airline runs a commuter flight that holds 40 people, and the airline knows that the weights of passengers plus luggage for typical customers on this flight is about 210 people, with a standard deviation of 25. And you could find that using data like from repeated flights, right? You do this thing enough, you have data for this. So draw a picture of this distribution. All right, so same kind of idea as before. The mean is in the middle. This is 210 pounds, yep. Not kilograms.
Well, you said
You
people.
said people.
Oh, I meant to say pounds. I'm so sorry. Thank you. Okay, and then one standard deviation away is plus or minus 25, right? 235 and 185, yep. Two standard deviations away is 260, is that right? And then 160 on this end?
So symmetrical.
Say that again?
So symmetrical.
Yeah, it is. And then we have 285 and 135. Okay. And it helps me to have a dotted line because that's like that's my mean or my like line of symmetry. So it looks about like this. So what this thing tells you is this tells you how much variation from passenger to passenger. And I guess they do have luggage, like they're counting the luggage in this weight here. Does that make sense? So it's almost like, so is it rare to have somebody who weighs less than 135 pounds get on a flight? Yes. More than 285? Yes. Okay, so that is rare. But this is from passenger to passenger versus averages. Okay, that's what the next thing is. So describe the sampling distribution of the mean weight of passenger plus luggage for a random sample of 40 customers. So what's different there? Did the mean change? Nope, the mean is still mu, which is still 210. Does the standard deviation change?
Yes.
Yes. That would be sigma over root n, which is 25 over root 40, which works out to be, I think, about 3.95. And this tells me how much their average weight will vary for groups of 40. And that's what they care about because every time they have a plane, they have a random sample of 40 customers, right? All right. So 68% of X bar fall in 210 plus or minus 3.95, which is 206.5. To 213 point, and I think I must have made a boo-boo. Should that be 206.05?
Yes.
Yeah, it should be. Okay, I'm so sorry. So 206.05 to 213.95. That's the average per passenger plus luggage weight in groups of 40. 95% in 210 plus or minus 2 times 3.95. Which is 202.1 to 217.9. Do your numbers match mine? Yes, okay. And almost everybody in plus or minus how many standard deviations? 3. I got 198.15 to 221.85. Yeah? Okay, great. So how do those intervals compare to the things we drew on the graph in part A?
Well,
They're way narrower. Do you guys agree with that? Okay.
you might overestimate by twice the rate.
Yeah, so that's like the thing in A talks about like passenger to passenger, right? This is if I look at a whole group of 40, what's the average weight going to be in that group? In which case you can find the total weight by multiplying the average by 40 people. Okay, that's like saying most of the time they're going to be, going to be extra careful. That's kind of like the worst case scenario, right? Everybody weighs a lot. So part C says to draw a picture superimposing the distributions from A and B, which means like together, right? And label it clearly. So who is going to be taller, the one from A or the one from B? B. Okay, so big, fat, horizontal line. Let's start with A. So 210, 185, 160, 135, 235, 260, and 285. And that one's going to be pretty shallow, or not tall. The other one, okay, the first interval is 2, so 19. So what's half between 185 and 210? 95. It's a distance of what, 25, 12 and a half?
192.5?
What, 197.5, I think, right? Okay, so 197, 206 is awfully close to 210 then, isn't it? And so 213 is pretty close on that side, isn't it?
So narrow.
Oh man, it's so narrow. Yeah, you don't even get to 185, do you? So it's super de-duper tall.
Super duper.
Super de-duper.
New words, yes.
I think Tigger said that.
Oh, did you? It's been so long since
I have a dog who we're gonna start calling Tigger because he's bouncy, 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 fun, 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 fun. Sorry, I just recorded that. Oh God, it's gonna go on YouTube. The point is, it's a heck of a lot taller than the other
Things
ones.
on the internet never die either.
No, things on the internet never die. Nope, I'll have kids and they'll go listen to the internet someday. It's gonna be great. Okay. So does the fact that this one's a lot more compact make sense though?
Yeah.
And since the total area must 1, it has to be a heck of a lot taller. That's kind of the main idea. It's just drawing them is fussy because I cannot tell you how tall they go because the formula is gross. Like there is one. I know what it is. I don't want to talk about it.
Trying to do those.
Okay, it's a 1 over E root stuff junk. Ugh, no. Okay, moving on. So, assume the customers on any particular flight are similar to a random sample. If the total weight of the passengers should not exceed 880 pounds, 8,880 pounds, what is the probability that a sold-out flight will exceed that weight limit? So what we're going to do here is change that 8,880 into an average.
You're adding 8 pounds.
I keep whatever, 8,800. Thank you.
And
No, 80, into an average. So, total weight is 8,800, or the average is 8,800 divided by what?
40.
Okay, without a calculator, knock off a 0. 8,800 over 4. Without a calculator,
220.
exactly, good job. I was just saying, like, you can do this with a calculator sometimes, right? It's possible. Okay, so that's the average weight of bean 220. So can you already say this is pretty unlikely? That's awfully close to the top end of this, the interval you found in part B, right? Okay, so we're gonna find the probability that X bar is bigger than or equal to 220. And what you can do now is that you can make this X bar into a Z value and use that Z tail of probabilities to figure this out. Because, okay, so remember how we had that Z was equal to, was it X minus mu over sigma thing, right? It's just that in this case, instead of X, we're going to use X bar. So our X bar is 220. What do we use for our mean?
210.
210. And the kicker here is you don't use 25. Okay, you don't use, you use 3.95. Do you guys see, can you think about why you do 3.95?
Because it's for the group of 40.
It's for the means in the group of 40, exactly. But it's kind of the same structure in the Z formula, isn't it? Okay, that comes out to be 2.53. So looking for the probability that Z is bigger than or equal to 2.53. Does your table do Z's in this direction? No, it goes less than, right? So how do you change this into a less than? 1 minus. Okay, and look at your tables and see if you can figure out what that value is for the, it should be awfully close to 1. Anybody dare to say what they get?
Like 0057.
You're looking on the negative side. Oh, you got the answer. I'm sorry. What did you get for this part?
Oh, 9943.
9943, that's the right thing. Good job. So 0.0057. So this thing that happened here, that's that whole complementing idea, right? Okay. Awesome.
I have a question.
Yes.
So why did we use 3.95? I understand like we wanted it less than 4, so why didn't we just use like 3.99?
Oh, no. This 3.95 we used was the standard deviation of X bar.
Okay.
So, like it was the number we found in example part B.
Okay.
So is this saying that it's there's a low probability of it exceeding the weight limit?
Exactly, which is good, right? That's how you want it to be not very likely that this would happen.
Wait,
There's a low chance. So if the weight limit is 880, that's the same as saying the average weight per person is 220, you buy that, right? And the probability that your average weight is bigger than 220 is the same as that you get a z-score bigger than 2.35, which is probability 0.0057, which actually, if you fly a lot of flights, might actually be too high, right? If you fly like thousands and thousands of flights, that will happen occasionally, and that is a problem, right? So you might actually want this to be quite a bit smaller to really guarantee this doesn't happen very often at all. 0.5%, but 0.5% of 1,000 flights is kind of a lot of flights, right? Or even,
1,000 daily.
yeah, and just think, like, even from Alaska, like, how many flights go to Anchorage from Fairbanks every day? Like, I think like 10, right? Times 365, right? It's quite a few. So, or up to Barrow. And of course, like, this average thing would vary based on your population. Like, I have friends who go up north to do field work, and they're biologists, but an average weight of a biologist compared to an oil field worker is actually quite different. Like, these big guys versus these, like, little petite women.
Versus what they bring also.
No, it really is, like,
Most
it's really small biologists versus, like, big guys working on the oil fields.
I know, but
But-
they also bring their equipment.
So yeah, anyhow, so there's lots of, the average thing depends a lot on who your population is. So, as opposed to people just like going to do business someplace. Alrighty. So, next. Means of paired differences. You see why I couldn't give a quiz today? It's just not possible. Okay. So, we had paired differences and differences in two population means. So our paired differences have to have an obvious pairing of some sorts. So for example, I swear I'm not, this is a diet, does going on the Atkins diet lead to weight loss? Do you see how there's an obvious pairing there? Like start weight minus end weight. You could do something like that for every single person. What is the age difference between husbands and wives? I just almost wrote wives. Oh my goodness. That's embarrassing.
Not in this country.
Which sorry. Will retain my rage. And I think that husband age minus wife age would probably more often than not yield a positive number. Not always, okay, but if someone's older, it's often the husband, right? Not always, I didn't say always, but often. Generally speaking, yes-ish. But the point is paired versus like average difference in age between men and women at UAF, two separate groups. Okay, pairs, separate groups. So the biggest thing in this section is, can you tell me the difference between, is something a paired thing or are they separate groups? So tell me which parameters being described in each of the following situations. So mu is just a regular old mean. Mu sub d is this whole paired difference thing. And mu1 minus mu2 is two sample means. Okay, so is the difference in the mean number of push-ups new male and female recruits can do, is that a regular mean, paired differences, or is it two separate groups? Two separate groups. You're not going to have like, it's not like brother and sister. Does that make sense? But it's like, what can the men do, what can the women do, then we'll compare them. So this is two groups, which is mu1 minus mu2. Another hint is that when you have two sample means, you can have different sample sizes. When you have paired things, you have to have a matching thing for everybody. So if you had male and female recruits in, like, I don't know, the Marines, are there going to be the same sample sizes? No. Heck no, right? So that's kind of another thing. We could even do this class. We wouldn't have to have the same number of men and women. So, versus this one, the mean change in the number of push-ups female recruits can do at the end compared to the beginning. Because that's an obvious pairing going on. So this is mu d. You would do the, I don't know, before minus after.
What do you want to do after the final?
Probably want to do after minus before. Because that probably will be, hopefully if you train, you get better.
Yeah.
Yes? Although there's no requirement that this mu be a positive number. Like as long as you tell me what you're doing, it's okay. Your book, when it has stuff like this, specifies what order for you to put stuff in. It says use placebo minus drug or something like that. It tells you what to do explicitly so that it can be consistent across all your answers. But it doesn't really matter. It's just nice to have positive numbers because they're easier to work with than negative numbers, right? Okay. So when you're talking about paired differences, what you do is you take some like before measurement, some after measurement. You find the difference. So one, take before, take after, find the difference, and then you average those. So if I wanted to do like average weight loss, I'd measure your weight before, your weight after, do before minus after, and then use the before minus after data to do the rest of the stuff. I forget about the other measurements and move on. Does that idea make sense? Okay, so do before, do after, find your differences, and now just analyze the differences, which came from the other stuff, but you can just ignore them for now. So the notation for the difference in two measurements is going to be d sub I, d for difference. And instead of x bar, we use, do you remember? We use d bar. Just emphasize that we found an average of the differences. As in, first we found differences, then we averaged them. So average of differences. What symbol? I'm sorry. I made a bit of a boo-boo.
Oh.
Write in pen here.
No, I'm sorry, scribble it out. That should be mu sub d. Because, can you tell me why why that is what it should be?
The mean of the differences.
The kicker is it says population. So it's the true value. I'm so sorry. Where should I have written d bar? Mean for the sample differences. So that this is d bar. I'm so sorry. I don't mean to do that and make it more confusing. So standard deviation for the population, do I use S or do I use sigma?
Sigma.
Sigma. Okay. The standard deviation for the sample, you use S. With a little subscript of D saying these came from differences. But that's all that's different, is that little subscript of D. Okay, so kicker, sample data. So the population, okay, so the conditions for this to be normal, and it's the sampling distribution of D bar now instead of X bar, but just means it came from differences. It will be, if this is bell-shaped, then you can pick any size, just like the conditions we had for last time, right? And if they're not bell-shaped, but a large sample is measured, and a common definition of large is a sample of n equal to 30. That, your other books call that different numbers, okay? That is the book's arbitrary definition of what is large. And if you have outliers, you should make an even larger sample, just to kind of like see if they're really like, not to decrease their influence, basically, is what you do when you get a bigger sample. Okay. So this is just like the regular mean case. So the distribution of the sample mean, in the regular mean case, the mean was just mu, right? This one is mu sub D. The standard deviation of X bar was sigma over root n for the mean case, right? This one is just sigma sub D over root n. Because your population didn't change as you took two measurements for everybody instead of one, right? And you found you have a sigma for that population of size n. So really nothing changes. Sorry for all the weight questions, but this is like a really good, like, before after measurement is weight. So suppose there is no freshman 15, okay? Who thinks freshman 15 is a lie? Okay, who thinks it's not a lie?
Oh, wait, I don't understand.
Okay.
Like,
Is the
believe it if it's not a lie?
Okay, do you believe the freshman 15 actually happens to people on average? Yes.
With 949.
Oh, yes, I think it happens. So we're gonna use statistics to explain why we think the answer is yes, okay?
What if you think they gain weight but not because it's their first year of college? Like,
Maybe it's just because you're still growing, right? There could be
Yeah,
other
exactly.
reasons, but the point is there still could be a freshman 15, even if it is because you're growing. We're not gonna say why.
What's freshman 15?
oh, it's a joke that when you go to college, you gain 15 pounds.
And
First
then
joke's
you
on you,
never
though.
lose
There's
it.
not-
And then you never lose it. And I think,
There's not many, I mean, they don't have a specific factor, but there's different factors that have been known to.
yeah, I mean, alcohol consumption probably is one. When I went to school at a residential college where people lived on campus, and there was a lot more junk food available, like, I ate stuff my mom wouldn't have let me eat.
Parents around to tell you.
Oh, yeah. Or it was just like, I have chicken nuggets every night. Yay, chicken nuggets. Okay, so.
Your parents are here to go, you can't eat this entire cake, and you're just like, no, yes, I can. Watch me.
And you could have cake sent to you for your birthday. Like, they'd make them in, okay, anyhow, moving on. Okay, so in an early example in this textbook, there was, somebody asked like whether students really gain weight, and they measured 60 students for 12 weeks, and they found that the average weight gain was 4.2 pounds in that group of 60. I don't know where this came from, but someone did this and this is what they got, okay? So we want to know, is it likely that the mean weight gain for a random sample of 60 students would be as high as 4.2 pounds if there really is no average weight gain? So like, was that 4.2 average weight gain special somehow, yes or no? And we'll have to do statistics to figure this out. Okay, so to answer this question, we need to know what to expect the sample mean D bar to be for a sample of n equals 60. Now, why do I assume mu d is equal to 0?
Because there's
No difference.
I'm assuming that there's no difference or no gain. And we are just going to pretend that that standard deviation is 7. Like, I don't know where they got this from, they just picked a random number, okay? So we have mu sub d equals 0. Find me the standard deviation of d bar. That's that sigma sub d over root n. That tells me how much variation I'm going to have in samples of 60. Assuming the population standard deviation is 7. So that's 7 over root 60, which is,
0.903.
I think I got 0.904.
Yeah.
Okay.
Just a quick question for notation on homework, because I know we talked about standard deviation being.
And standard error.
Yeah. Do you
So
want,
you-
how do you want notation?
It's standard error if you use S sub d.
Okay.
It's
so-
standard deviation if you use the actual
Yeah,
sigma.
I was
Does that make
wondering,
sense?
like, when we're writing it down, that it's standard deviation of D bar.
Yes, I would like to see, yeah.
D bar.
Because otherwise it's confusing because you have this other sigma that is standard deviation as well. So I think it's probably good to write SD of D bar. Yep. Okay, so what that means is that 68% of D bar is in 0 plus or minus 0.904, right? What is that as an interval? Negative 0.904 to 0.904, exactly. And the negative 0.904 means that freshmen might actually lose some weight, right, as opposed to only gain. 95% of D bar is in 0 plus or minus how many 9.04s? 2. Which is negative 1.808 to 1.808. And almost everybody zero plus or minus how many standard deviations? 3. Which is negative 2.712 to 2.712. So D bar equal to 4.2 is in the top fill in the blank percent. So with this last one, 9.7, there's 0.3% left, right? Half of it falls on the bottom end and half of it falls on the top, right? So they're in the top how much percent?
0.015.
0.15, just 0.15. So do we think so that's kind of unlikely, right? So this means that the freshman 15 is probably real for most people. I didn't say, like, there was a Y or anything, or that everybody gains the freshman 15. Nor did I say it was 15 either, did I? And that was 4.2. The freshman 4.2 just doesn't sound as catchy as the freshman 15. Sorry. Okay. All right, you ready? Okay. One more. We got time. All right, so here's one that isn't about weight gain. Horn, Reiner, and Barrett describe a study in which 12 men took a simulated driving test after drinking alcohol at lunch, getting too little sleep the night before, neither or both. So they're comparing a whole lot of things, but they got these poor guys, I don't know how much they made them drink either, but hopefully it was only a few drinks, and hopefully they kept them until their BACs went down. And each of the men took a test under all 4 conditions. One of the measurements taken under each condition was the number of times the drivers drifted out of his lane during the 2-hour test. And
2-hour test.
I know, right? Isn't that
Really
crazy?
dark. We went from gaining weight to alcohol consumption.
We did. It's your textbook's fault, okay? I can't make stuff up like for this is easy.
This is real life.
This is actually real life. I mean, this is why they set BAC levels where they set them. It has to do with when people start to make mistakes at a high enough rate that it's likely to happen. I mean, unless you're in Sweden, in which case they just say nothing. Like, you can drink nothing and drive. So, consider, in this one, they measured a lot of things here. They measured for what we know, they have drinking alcohol, no sleep, or little sleep, neither or both, right? So they measured 4 things. So we're just gonna look at the mean difference in number of lane drifts between the condition with alcohol but sleep and no alcohol but too little sleep. So that's just those 2 things. So it's kind of like saying alcohol alone and little sleep alone. There are lots of other comparisons you could make, but this problem is just looking at comparing how does alcohol compare to getting too little sleep in terms of, affecting your driving? Okay. So kicker is, are we going to have a pair of measurements for every person? Yeah. So we want mu sub d, the difference in number of lane drifts, or times they leave their lane, with alcohol minus number of lane drifts with little sleep. Do you buy the proposition that alcohol will cause you to drift more than not sleeping? It depends. I think it depends on how much alcohol, right?
I've heard that it can actually.
Sleep is bad too, okay? But the point is, they are both bad.
Actually equivalent to alcohol content in the body.
One more thing, I don't hashtag, I pound sign for number, that's okay, right?
Yes, that's
It's
okay.
not a hashtag, okay.
Hashtag lane drifts.
Hashtag lane change. Describe the sample statistic of interest in the context of this situation. So the parameter was mu sub d. The sample statistic is d bar, which is the average. So the mean difference. In number of lane shifts for size n equals what? 12. Great. Do you understand why we use d bar here and not mu d? So because it was the sample versus the parameter, which is population, right? Okay, spectacular. So given that the sample size is only 12, we haven't met the big enough condition, have we?
No.
Okay, so if we're not going to have a big enough sample, we have to assume that our population that we have underneath this is bell-shaped. Yep. So we assume the population of differences must be bell-shaped. Okay. If your size is bigger than 30, you're kind of okay if it's not bell-shaped. Suppose that getting too little sleep and drinking alcohol at lunch have the same effect on the mean number of lane drifts during that 2-hour time period. And we assume the standard deviation for the population of differences is 5. Describe the sampling distribution of a statistic that you gave in B, assuming that your situation in C holds so you can even talk about it. So when they say describe this, what they really mean is they want the mean and the standard deviation of that sampling thing. So the mean, mu sub D, if there is no difference, it's going to be 0. And then they want SD of D bars, the standard deviation, how much will my average lane drifts vary? And that's this sigma sub D over root N, because in samples of 12, right? Not just for individuals. So what's that, 5 over root 12, which ends up being about 1.44.